This is lecture 4 of the course, the lecture set, Finite Group Theory at junior and senior level. And the principal, the first author of the textbook that I'm using is Barnard. And once again, here's the book that I'm using. It's in the Teach Yourself series. And the title is Mathematical Groups. And if you want more details about this text, how to get it, its price, how to get it for free from email and so forth, go to this website. So Prof. Hugo deGaris, that's my name, professor.wordpress.com. Okay, so lecture 4 on integers. And this lecture is, in a sense, the last preparatory lecture before lecture 5, which is on groups, because I mean, after all, this whole lecture set, this course is on group theory, or finite group theory. Finite in the sense that now a group is a particular kind of set. So a finite group is like a finite set. So there's a limited number of elements in the set or in the group. Now you can have other kinds of groups that are not finite, so you can have continuous groups where there's effectively infinite number of elements in the group, so they're not finite groups. But so this is about finite group theory, which is large enough. Okay, I guess I should warn you. There's a warning is needed. This particular lecture maybe, it's certainly one of, but it may be the most difficult, the most intellectually demanding, toughest lecture of the whole book, the whole course. Why? Because it's about the theory of integers, and the usual term for theory of integers is number theory. And number theory can get quite difficult. This lecture will be full of proofs, theorem, proof, and the proving at times gets quite difficult. So you'll need to put on your thinking caps and concentrate. And if you, general comment, if you can't follow something, if some notion, some concept I introduce that you haven't a clue about, your brain's just totally unfamiliar with the concept, and so it just washes over your head. Doesn't matter. This is a videoed lecture, right? So you can rewind. You can go back and you can replay. You can replay the section that you don't follow easily or well as many times as you like until your brain does become familiar with the concepts, and you do see the logic at every step in the proof until you can go right through to the end of the proof and understand it, until it clicks, until it becomes almost intuitive. That's the huge advantage, the huge plus of videoed lectures as contrasted with traditional real-time classroom lectures. So if you miss a point, too late. I mean, the professor's moved on. But with a video lecture, you're the boss. You can control the rate at which you absorb this stuff. You can rewind as many times as you like, and so on. Okay. Alright, so the usual format, the main points a bit on the left, on the right here as well, because this may be a rather long lecture, because a lot of proofs. So, as I said, be warned. Okay. Alright. Now, why? Maybe I should justify a bit. Why integers? Why are we talking about the integers in a group theory course? Because theory of integers is number theory. Usually. So why integers? Why talking about numbers? Because some of the concepts in this lecture will definitely be used later, in later lectures in this course on group theory. So in a sense, this lecture is a kind of tools lecture, a preparatory lecture. Particularly concepts like the division algorithm. Don't worry. You don't understand yet what they are, but these are sort of the main concepts, main themes for the lecture. Division algorithm, the concept of relatively prime numbers, the idea of what's a residue class, Two numbers can be congruent. What does that mean? The arithmetic of residue classes. Yeah, they're the main themes. So we'll do all that this lecture. So by the end of it, you should be fairly familiar with these concepts. And these concepts will get used later, okay, in later lectures on group theory. So to understand some of the ideas of group theory, we will actually use some of these concepts. So you need to know them. All right, so let's start. The well-ordering principle, PR for principle. What is that? Well, it's almost so intuitively obvious that you don't really think about it. And so this well-ordering principle gets used a lot as an axiom. Something you start with that you feel is so obvious that you don't question it, you just accept that it's true and then use it to make conclusions in a mathematical argument. And what it says is that if you have a set of integers, one of them will be the least. Now that's sort of duh, right? It's so obvious. So, or you can rephrase it in the sense like every set of integers will have a smallest member. Okay, seem reasonable? Now, this well-ordering principle, what I just said, will pop up a couple of times in the future lectures on group theory. Right. The division algorithm, used quite a bit. What does it say? Well, you have, let's see, you have an integer that belongs to the integers. You have a number belonging to the integers, A, and you have another number B that belongs to the natural numbers. Okay, so the positive integers. So I could put it that way. So the natural numbers are just the positive integers. Okay, so for those pair of numbers A and B, you can actually rewrite A using B in the following sense. A equals, I don't know, call it, what do they do in the text? I'll try to keep the same as the text. Uses Q, right? QB plus R. You can write A in that form. And Q is an integer, okay? And R is the remainder. That's why you use the letter R, the remainder. What's left over after a division. So R will be greater or equal to 0 and less than B. Okay? Let's do an example. Let's say A is 27 and B is 12. Yeah, whatever. So I can rewrite A in the following way. So A, which is 27, is some integer times B, so some integer times 12. So how about 2 by 12? So B is 12. So 2 times 12, that's 24 plus 3. Okay? So 3 is the remainder. Or, given that we're going to be talking later about residue classes, that 3 is the residue. So residue, remainder, same thing. Okay? Why residue? Well, in ordinary English, the residue is sort of like what's left over. For example, in the context of chemistry, if you boil off some, say, a flask of seawater, so once the water has vaporized off, boiled off, what's left will be the salt from the salt water, okay, the seawater, and that salt that's left is called the residue, what's left over. So by analogy in mathematics, when you divide, so if you're dividing this number 27 by 12, right, you'll get the answer 2, and something left over. which is the residue, right? So, or the remainder, same thing, right? So the residue here is 3. Okay, now, two integers are relatively prime if the following is true. So let's say you have two numbers a and b, and if I put rel RELPR in front, that's my way of saying that these two integers are relatively prime. So a and b are relatively prime. And what does that mean? No common factors. You can't divide both of them by some integer, other than 1, of course. You know, that's the exception. But that's sort of a trivial case. So if a and b have no common factors, you can't divide both of them by some integer. So no common factors. If that's true, then a and b are said to be relatively prime. Okay? Let's just do a couple of examples and counterexamples. So 4 and 3, do they have a factor in common? No, other than 1. Right? No. So 4 and 3, they're both integers, and they have no common factors, so they are relatively prime to each other. Okay? How about this one? 6 and 9. Are those two integers relatively prime? No, because they do have a common factor, 3. So 3 divides into 6, and 3 also divides into 9. Okay, so 6 and 9 are not relatively prime. All right, now I think that's fairly clear. Let's start now on some theorems, and suddenly, be warned, you'll notice the standard goes up. So let me clean this off a bit. I need some space.